Let's start from the Chinese. So you are given 10 minutes.
Good morning, everyone. The paper I present is an update-aware storage system for low locality update-intensive workload. The outline is like this. The motivation is traditional storage system is not good for the update-intensive and low locality disk access workload. Many papers try to work with this problem, but there is not good performance. When under conditional interface, existing storage system optimize disk write access by delaying and scheduling them to maximize their throughput and optimize read operation to have optimize the disk read access by serving them as soon as possible. But when the application like database management system or file system request to modify access, they must read first and modify them and write it back to the storage system. But modification access consists of 3 steps, so it may be treated as soon as possible because they storage system trying to read as soon as possible. So they propose the new storage system architecture, BOSC. BOSC means batching modification with sequential commit. It exists between storage application and hardware storage system. And they propose a new function modify. They eat the BOSC system based on the trail, a previous work called trail. So let's look trail first. Trail disk architecture has used logging system. When write access arrive to storage system, the controller when write request is come to storage system, the disk have to find the block address, so it has long latency. Instead of that, one of the disk is used for logging log this disk. When write access is come to this logging system, they write the request into log disk. The header is happen to be, so they hidden the latency.
It's not clear. So what's the function of this log disk? So you have main disk and log disk, and what is the function?
As you know, main disk store the every data, but when write access is approached, they must the main disk must find the actual position in the disk. So it needed the time. Instead of that, the log disk log the access request. The header happened to be.
Not clear.
Okay.
It should be simple. So can you explain simple? You have to see the picture, not your script. You have to explain.
I'll draw.
Okay.
This is the location we want to write. So we have to find the header rotation to get this position.
Okay. Find means the seek time and rotation relationship.
Yes.
Okay.
But this is main disk, and this is log disk. They log the write request. The header is happen to be here, not
What do you
rotate.
mean by have to be? I don't know. So main disk has data.
Yes.
Low disk has what kind of information?
The data which is will be right, and when it is come something like that.
So your English is not clear. So what do you mean? Is low disk has some history or the future request information or what?
The request they get.
So there is a incoming request.
Yes.
Okay, incoming request contains disk address and data.
Yes.
Okay, if it's for write. If it's for read, it just has disk address.
Yes.
Okay, this request information, it does not go directly to the main disk. It goes to the low disk.
Yes. Because when it go to main disk, it have to wait some time to find the.
So you
location.
cannot avoid this disk seek time and rotation latency. You have to spend latency. What do you mean by you have to wait? You have to wait anyway.
They predict this header.
What do you mean by header?
Disk
So disk operation is seek time means you have to disks are concentric circles, right? It's called track. So this disk count should move into the right track first. That is called seek time, and then this track consists of multiple sectors, many sectors, and these are rotating. So you have to wait until the right sector is on the very top of your read-write task. So you have to wait its rotation latency. It's usually half of the one single rotation time on average. And then you can read the block while you're rotating. That's called transmission delay. That's quite fast. Okay? And he's saying about the delay of the seek time, which it takes the most of time because this is mechanical movement. And then rotation latency. What?
They predict the head position, and they write the right request, the location the head position is.
You're skipping something. Okay? So what you are saying is they are writing for write operation, they are writing to this log data is log disk instead of main disk.
Yes.
Okay. And how about the read? Do they still require to access the main disk or log disk?
I'll explain right exit right.
Okay. No. You have to give some picture. So in the log disk, it's mirroring the main disk, or it's just storage for this update only.
Update only.
Update only. Why? And it looks like just by predicting can accelerate this seek time and rotation latency. Okay, and that's the only advantage. They just predict, so that reduce the seek time and rotation latency. But some of the data are here, some of the data are here, because you write here, but most of the existing data is here, right? And there are some issues.
Okay. They write log disk first, and they queue the data on this DRAM buffer.
DRAM buffer is separate, so while you are writing to the log disk, you can also write to the DRAM buffer.
Because they
DRAM buffer is it's not the disk, you can write fast.
yes.
Okay?
DRAM buffer is divided into some area that the area is correspond to some main disk sector or like
So
that.
you update main disk later,
yes,
and you can combine this update in the DRAM buffer.
yes, scheduling.
Okay, what if your prediction is wrong? So you predict your arm location, right, to reduce the stick time, okay? Sometimes your prediction is wrong, then you have to move back and forth. What happened?
In log disk.
That's right, because you said they are predicting the location of the arm, disk arm. Right? What if their prediction is wrong? Incorrect prediction, what happened? And for read operation, usually you have to access main disk only. But for this kind of system, you have to access, depending on the data, you have to access main or log disk. And you have to,
just access DRAM buffer.
right, you have to access DRAM buffer or main disk.
Yes.
Right? Some of them are duplicated. And you have to maintain that directory somewhere, right? So there is some overlap. And for misprediction, you don't know. Okay, so this is the old architecture for updating. That's what they're saying.
This is for hiding the latency.
Right, but is this author's proposal or previous proposal?
Previous
That's
proposal.
right, previous proposal.
Yes.
And what about the right picture? What?
This is another
Another proposal.
yes.
Okay, so explain.
And using this trail disk architecture, they
No, you have to explain. Look at the picture and explain. What's the difference between the left and right?
the one is the all controlling is by the hardware,
Okay.
and right one is this is by software,
Mhm.
so that's different.
No, it's not enough. We don't know the idea of the second existing proposal. What's the idea? You don't know the detail.
This is same trail.
So they don't show this log disk in this picture. So what's the difference? We don't know.
When it has many disks, they separate disk as log and main by software.
So they use the same single disk, but inside the single disk they separate main section and the log section. Is that right?
I don't think so.
So what? Then what?
If they have 3 disk hard disk driver, they use one as log disk and use 2 as main disk by
So
software.
in terms of hardware configuration, are they same or different?
The algorithm is same.
I'm not sure. What do you mean by algorithm?
Logic.
You are not giving enough detail. So using the left picture,
Yeah.
what's the difference? You said they have main disk and log disk, and they have controller and DRAM buffer, and they have these 2 queues. What are the difference? Can you explain?
The left one is
What was the problem in the left picture, And what the second idea is trying to solve.
And it's not the paper purpose.
What do you mean by it's not the paper proposal? That's what you said is that's the previous proposal, right?
Yes.
Okay, so explain the previous proposal. You don't know. If you don't know, then skip.
Okay.
You don't know.
This is come from same.
Author,
Yes.
but you don't know. You don't know the detail.
Yeah.
Okay. Skip.
And this is performance, but I'll skip it. And this is the author's proposed architecture. They suggest to modify request. So file system or data file system database management system can access disk use modify request. The both get modify and read request and write request, and both schedule the modify and read request as trail architecture. They write the two requests in log disk.
You have to look at the slides, not your script, and I cannot follow. And you have about 5 more minutes, 8 minutes past. Okay. So within the slide, explain. You are given 5 minutes.
Okay, this
So
is
there are pointers. You should come to the here. Explain. 5 minutes. What's the idea of this paper?
the idea is simple. When modify requests come from the higher layer, they write modify request on log disk, and they queue on the disk queue buffer and scheduling them. And when the main disk block is go in memory, the all requests in the disk queue are done.
Not clear. You said it's simple, but to us it's not clear. So how do they solve this read, modify, update cycles of this existing storage system?
Modify has 3 arguments: the target, block address, and the modification data, and the function when it will be in the main memory.
What's that function?
Function means if modify is insertion, the pointer commit function point to the insertion request.
Okay, so what kind of functions do they provide? Insertion is one type of modifier. What other functions?
And delete?
Insert, delete, and then what? Update?
Yes.
Okay. So
Using these 3 arguments, this is disk queue, which is contain the request onto some area, disk's area. So when this disk are go into main memory.
What do you mean by go into main memory? You request modify. It can be insert, delete, or update. And there is a queue. Either insert, delete, or update. Okay?
Yes.
And you just set
Even if they have that information, it must be into main memory to do this function. So when, for example, the read request come to the BOSC architecture, the area will be go into memory because it is read access.
what do you mean? Read some different read requests should read, needs modify or insert or new data, or what do you mean by read?
Any read request to the any point of this block, then it will we can think like this cache line when the read request.
Same as any other disk buffer. So disk access can go directly to the disk drive, or this disk buffer, actually if you hit the disk buffer, they can provide the data directly. So because you are buffering your request and the data, the request can hit this disk buffer also in this architecture, and it's not different from any other architecture.
The main difference of this architecture and other architecture is they can know the modify request so it can be scheduled.
Not clear. What do you mean by they can auto-modify?
A traditional storage system, if they want to insert some data, they must read disk block, and the modify is processed in main memory and come back to this disk block. But with BOSC, they insert access using modify, so they can be scheduled modify, and when disk access when the access is access to this disk block, they send all requests in this queue and they process it sequentially.
Okay, somehow I feel like what you're saying is they used to have read, modify, or all kinds of requests coming into the disk drive, and sometimes to do that they have to read the disk drive into main memory, and they have to do that operation, and then they go into this disk buffer and so on. But they have all this information already in the disk buffer, so they don't have to go back and forth. And whenever the new request comes in, they can analyze this queue, and then they can do the operation standalone in the disk drive. That's what you're saying, right? No?
They don't do in disk drive.
Okay, we don't have much time, so you are given maybe, so past about 25 minutes. Okay, so you have, this is 9:46, I'll give you 4 minutes in Korean explain. We don't have time. Excuse me, sorry. 한국말로 정확하게 얘기해. 뭐라고 얘기해?
기존에는 modify하는 리퀘스트가 들어오면 리드의 프라이어리티가 있기 때문에 이게 빠르게 오지 않아도 되는데 리드를 하고 해야 돼서 먼저 이거에 모디파이에 된 게 메인 메모리에 올라가서 디스크에 그 트루풋을 좀 많이 잡아먹는 경향이 있었는데 그러지 말고
왜? 리드가 더 중요한데. 그리고 프로세서에서도 리드를 빨리 하고 리드를 빨리 하는 게 스루풋을 증가하는데.
예, 리드가 중요하긴 한데 모디파이 된 거는 이 값을 읽어서 저희가 사용하는 게 아니기 때문에
그러니까 프라이어티를 낮게 줘도 되잖아.
그럼 리드에 프라이어티를 낮게 주면은 다른
모디파이 프라이어티를 낮게 준다고.
근데 그거를 기존에 있던 하드웨어에서는 할 수가 없었습니다. 왜냐하면 이게 모디파이인지 그냥 리드인지 알 수가 없었기 때문에.
알 수가 없었다고? 왜 몰라?
왜냐면은 아까처럼 뭐 그러니까 모디파이 하는 명령을 하기 위해서는 그 파일 시스템에서 먼저 읽는 명령을 보내고 그걸 읽어와서 고친 다음에 다시 쓰는 작업을 했습니다.
그러니까 모디파이라는 어떤 새로운 트랜잭션이 없고
예.
항상 그걸 분해해서 리드 한 다음에 메모리 안에서 뭘 한 다음에 그 다음에 그래도 업데이트 해야 될 거야.
쓰는 작업.
스토어는 해야 될 거야, 그렇지?
예. 리드 모디파이.
분리했었는데 이제는 모디파이라는 작업을 줘서
예.
구분해놨다 이거지.
예.
그게 유일한 아이디어인가?
여기서 제공하는 유일한 아이템, 제일 큰 아이템.
다음 슬라이드.
이거는 그냥 백그라운드로 넣는 건데 이런 B 플러스 트리를 이용해서 그런 이 보스크에서 필요한 작업을 하기 위한 임플리멘테이션을 얘네들이 했다는 것을 알려주고 있었고 이게 이게 성능 분석입니다. 이게 보스크를 이용한 것과 그렇지 않은 것이랑 비교했는데 메모리 트루풋, 그러니까 하드디스크의 트루풋이 이렇게 증가하는 것을 볼 수 있는데
왜 이렇게 많이 증가해? 설명해.
예, 이거는 근데 로그 디스크를 쓰지 않은 것입니다. 아예. 만약에 로그 디스크를 썼다면 라이트 레이턴시가 하이드 될 수 있어서 아마 더 증가할 수 있었는데 얘네는 그런 거랑 비교한 게 없습니다.
비교한 게 아니지, 그치?
예.
하드웨어도 다르고
예.
아주 제일 기본적인 거랑 비교한 거야.
예, 예.
이 데이터가 다야?
일단 다 기존의 거랑 분석한 건 이게 다고 이건 여기서 자기네들이 그 디스크 블락 Q랑 뭐 버퍼 이런 사이즈 조절하면서 한 분석밖에 없습니다.
그래서 내가 분명히 얘기할 때, 이 프레젠테이션 할 때, 그전에는 모디파이라는 오퍼레이션을 지원하지 않았다. 그걸 분명하게 얘기했으면 굉장히 쉽게 들어왔을 텐데, 그걸 얘기하지 않고 뭐, 영어도 좀 서투르고 하니까 이게 이해가 안 되는 거야.
예.
오케이? 다음 거.
Hello, I present a paper about performance and energy implications of many core caches for throughput computing. Authors are C.J. Hughes, C. Kim, Y. Chen in Intel Labs. This paper was presented in IEEE Micro 2010.
So IEEE Micro Architecture Conference or Microjam?
I think it's journal.
Journal, okay.
Throughput computing, which focuses on maximizing the throughput rather than latency, is gaining prominence, and it involves a huge number of calculations with parallelism. Yes. The research objective is authors is designing many core caches for throughput computing, which considering power and performance.
Okay,
These tables authors use to evaluate their cache designs. Working set size means benchmarks using working set size with 64 threads runs. And authors use level 1 cache with size 32 kilobytes and level 2 cache to 256 kilobytes. Application whose working set size is bigger than 256 kilobytes shows slower than their original working set size. And cache miss rate column means error cache miss rate, which means high miss rate means high lower level cache access rate. And prefetch coverage columns means percentage reduction in error misses when straight prefetcher added. In high reduction rate like this means strong streaming patterns.
So is this for instruction or data? Cache or both?
I think it's both.
Both?
Yes. No. Data streaming pattern.
Stride means usually for data.
Yes. Figure shows the degree of sharing for each benchmark. Sharing degree for cache line is the number of cores that access that lines at the L2 cache. Authors separate read shared line and read write shared line. Read write shared line means access with at least one write request.
Okay, let's look at this figure. 1227R, 8263R, 64R, 227 read write, 8263 read write. So basically, one or read write. One is one.
One means private
core?
line.
One core.
Yes.
Okay. And 227R is read by 227 core.
Yes.
Okay. And 227 read write is read and write by written by 227 core.
Yes.
Okay. So there are quite amount of private data.
Yes.
Is this for integer or both integer and floating point or floating point?
In each benchmark there are different portion, I think, because also
No. What this application came from splash benchmark. Okay.
Yes.
This is for parallel application.
yes.
It's usually for more floating point application. Okay. Okay, that's that. Okay, sharing degree and spatial domain. What is spatial domain?
Portion of number of shared line versus total cache line.
12 out of 15 benchmarks has more than 17. Non-shared means private.
Yes.
Okay, so 70% of them are private.
Yes.
Okay, frequency domain.
In these bars, usually portion of number of cache line, shared line is smaller than access count of shared line.
Frequency larger than percentage spatial domain. So you have spatial domain and frequency domain. Spatial domain, you said, is private portion versus shared portion.
Yes.
What is frequency domain?
Total cache line accesses and shared cache line accesses.
Okay, so how much of them are shared out of total number of access?
That's spatial domain.
Okay, so what is frequency domain?
They count accessing cache lines. Is total that is 100%, and
Example.
yes. If 25, if shared line is accessed by caches, by cores to 25 times, and total cache access, which includes private line and shared line, are 100 times. That means in this graph, lines per accesses means 25%.
That's complex. So for each benchmark, we have two bar graphs, okay?
Yes.
And why do you have two bar graphs instead of one? Left one and right one.
Also thinks if one cache line, one shared cache line, there can be many accesses, not one accesses.
I mean, private cache line, there can be also multiple access. Shared cache line, there can be multiple access. So there can be frequency,
Yes.
to my opinion, means some of them are accessed more frequently than the other.
Yes.
Okay? It can be either private or shared.
Yes.
Okay? So the portion is, spatial domain is private versus shared portion. Just in number of lines, that's static count.
Yes.
Okay? And frequency domain should be dynamic count. Right? Even though statically there are more private sections, if shared sections are accessed more frequently,
Yes.
then total dynamic count, there are more different percentages.
Yes.
Is that right?
Yes.
Okay, so spatial domain, frequency domain, both of them are dealing with this ratio, and one is frequency and the other is static.
Yes.
Okay,
Yes.
and so 12 out of 15, so they are looking at how much private ratio. Okay. The ratio is, they are looking at the private ratio
Yes.
for both. Okay. And how about the picture, left picture and right picture? One is private and one is spatial and the other is frequency, or what?
Yes.
Okay, so left is spatial and the right is frequency. Right?
Yes. This in vertical graph, vertical bar.
Right.
Right. Left side is lines, which means spatial domain, and right.
Okay, but
is
frequency.
frequency
So
domain.
even though, let's look at the first one, this bar is benchmark, and private section is almost 70%. But if you count actual frequency, dynamic count, private portion access is only 20%. Is that right?
Yes.
Okay, that's right.
Author suggested some cache designs under these three constraints. First one is two-level caching. We just use level 1 private cache for each core and last level cache which is shared or private. Second one is directory-based hardware cache coherence. Directory-based coherence cache hardware is used for scalability issue.
But that's scalable only up to about 100 processors, not more than
Yes.
It's just medium scale cache coherence mechanism.
So also in simulation they use 64 threads only.
Okay, that might be mentioned.
Third one is tiled design processor. Each core and each Aaron cache and partition of last level cache and directory is in one tile.
What is tile?
I can't find about information on in this paper, but I think in CPU, in dual core, these two core and one cache and shared L2 cache.
What is LHC? LHC is L2?
Yes.
Okay.
These are ordinary dual
Okay.
core, but authors tiled design means here also cache controller, I think, but authors in many core and Aaron cache and LLC and directory controller and directory. These are all
How about
partition.
L2?
Authors suggested just using last level cache only and Aaron cache.
Okay, because L2 is more like shared structure that becomes part is centralized. That's what they're arguing.
Author just said it's too complex.
Okay, usually shared means it's not scalable. Okay. So it's more distributed. So okay, so tile is what? Tile, this kind of structure is tile or?
Each of this structure called tile, I think.
Each core is tile. Core plus caches, then directory.
Yeah, cache and directory.
Okay.
In this, in author's design, flexibility is key design criterion. Flexibility regards where a given line can reside in the LLC. It affects the critical path. Flexible design affects these characteristics.
Okay, so flexibility means, okay, you can divide the data into private and shared. Okay?
Yes.
And the flexibility, what they mean is some of the cache line can move between private section to shared section and back and forth. Is that right?
Private section, flexibility means in each LLC there can be only one line, unique line, or there each LLC has which is accessing that line has replicas of that line.
So you mean they allow duplication or not?
Yeah,
It's
duplication. Duplication of shared line.
Okay, so do they allow, if they allow duplication, then it means flexible.
Yes.
Okay. So there are two issues, in my opinion. Flexibility is you can divide private section and shared section. There are two issues. One is how much you allocate for private, how much you allocate for shared, which means in this architecture, how much you allocate for L1 and how much you allocate for LLC. Okay, that's one issue. And because the private section is varied depending on the application, and the hardware should run every application. The other issue is a single cache line can change from private to shared because it can private for this kind of execution phase, and for this there might be sharing, and for later phase they go into private. So single cache line you can give different flavor. It's shared or private, you can change. That's what I think was flexibility, but it's different, as you said. It's duplication.
Yes.
Okay, and today talk about these issues what I mentioned.
Pardon for previous talk.
Two issues. One is how much do you allocate for this cache? You can fix this private section and shared cache. The size of L1 and LLC.
Yes.
If you fix, some of them are too much private, but you can put all this private into your private section because you statically allocate. Okay?
They fixed L1 cache size and LLC cache size.
Okay, so they use static partition. The other issue is one cache line can change the flavor of private or shared, as I explained during the execution phase. Okay, and do they allow?
It's different to design. Each cache design.
I mean, do they allow this kind of flexibility proposal?
Yes.
Yes, they allow. So some cache line can move to LLC or move to L1 back and forth.
There's no transfer between L1 and LLC. Just using shared data is only using in LLC.
Right. So that means they don't allow this kind of flexibility, dynamic change.
Yes. But a private data can use LLC and L1 cache.
It's possible because private data can reside in any level of cache because either they maintain coherence or not, it doesn't matter.
Yes.
Okay, so private data can go up to there because hardware already exists.
Yes.
That's obvious. Okay.
More flexible design, which allows duplication.
So what do you mean by if they don't allow duplication?
Yes.
Then what do you mean? It's somewhat strange because most caches, if it's shared, then they allow duplication. That's why they maintain coherence.
Yes.
So for this architecture for LLC,
Yes.
even though they maintain coherence, sometimes they do not allow duplication. Right? And why? And what's the benefit?
Don't allow duplication. When don't allow duplication, total effective cache capacity is bigger.
Right.
Yes. So
That's the only purpose.
yes.
But the latency will be increased because you have to fetch from remote because you do not allow duplication.
Yes. But author says because our design is for throughput computing, latency doesn't mean a lot in their
So
benchmark.
they choose capacity or cache hit rate instead of the latency. Okay, and this might be okay for a single CPU chip, but with multi-CPU, right? Multi-CPU chip, each CPU might contain 8 cores, and with multi-CPU there might be 100 cores, and you have to fetch some data from remote cache CPU. It takes a lot of time. So So you pay quite amount of latency instead of you increase capacity, right?
Yes.
So I'm not sure whether that's good or bad, right? Is that right?
In their simulation, less flexible design with no duplication has better
So I can
performance.
argue that if you allow duplication, it's more flexible, and they do not allow duplication for some to increase capacity. So they actually decrease flexibility somehow, to my opinion, because naturally most processors allow duplication by themselves because you can cache any core can cache, but they don't allow cache because you have to use remote because you don't allow duplication for some shared cache line, right? You
Yes.
pay latency, so it's not flexible. Even though they are arguing that it's flexible, it's not flexible design, right? That's my intuition.
Yes.
You agree?
I think it's not really flexible.
It's not really flexible. Okay.
In access latency and on-die bandwidth usage, more flexible design allows duplicate.
What is more flexible design?
Allows duplication.
Allows duplication. Allowing duplication.
And number of unique lines, and which means high hit rate
Right,
ratio
right.
and
Understood.
off-die bandwidth usage and effective cache capacities is better in not allocate duplication.
Agree.
First, these designs, there are no. These designs are not authors' previous paper. I think it's used in past.
So it's previous proposal
Yes.
by another author.
Yes, I think
Okay.
there are no mention about it. The first one is private cache design. It says cores accessing data to on private LLC. Duplicated data can be resided in whole LLC. It has less unique cache lines. In paper, also use home tile, which word home tile. Home tile means is a tile which is mapped by address hashing function. Tag directory.
So
Yeah.
here private means it's physically private or it's private that we discussed before. Is it private? It's used only by this core or what?
Used only by this core, but can use cache to cache transfer by tag directory.
So it's actually shared cache line.
Yes, actually.
Shared cache line. So because people, if they have this local data, local cache, even though it's shared, they call it private.
Yes.
It's actually shared, right?
Yes.
And it's shared. And that's why they have directory.
Yes. I think author says private LLC means using cache to cache transfer, and the private like shared design means just to cache to register transfer. I think.
Cache to register.
Just to-
cache to register.
Just to read from cache directly. Not write to cache LLC.
Okay. Anyhow. Okay.
Tag directory of home tile, cache line home tile. Skip.
This is not.
Yes. Private design has three
This is
features.
also previous proposal. Right?
Yes.
Okay. Skip. Let's go to their ideas.
Before show their idea, we have to the author shows their simulation results.
Okay. So what they compare?
They compare performance and energy consumption. Let's see for performance first. You can the first one private design, uncontrolled replication design, which means unlimited duplication. and control replication using limited replication and two cache line to evict cache line. They use least recently used scheme. Yes, and no replication. Just using they don't allow replication. And shared design means shared like this design, this figure totally shared L2 cache, last level cache. Last one is tag directory buffer, is author's suggestion.
Okay. And what's the average? Do you have average? The rightmost column is the average.
Yes.
Experiment. Okay.
Last one is tag directory buffer, shows best performance.
Okay, so it's speed up. So compared to what?
Compared to shared design.
Shared design. Shared design is what did you say? L2.
Yeah. Shared
L2.
last level cache.
Shared L2.
Yes.
Okay. Compared to shared L2, how much speed up of their proposal? 1.1. 1.3% only.
Yes.
Okay, and the private only is 8% slowdown.
Yes.
And uncontrolled duplication is how much slowdown?
7 points.
7% slowdown. And no replication, how much?
It's same to shared design.
Okay. So no replication, shared, or their proposal are all about the same. 3%, sometimes it's garbage.
Yes.
Right? And then it's more complex than no sharing or sharing. Right?
Yes.
So, okay. So this is the performance. How about the energy?
In energy consumption, shared design means 1.00, but
So all the other can reduce the power consumption,
yes.
energy consumption. And how about this no duplication?
No
How much
duplication
can reduce?
shows 39%.
39%.
Yes.
How about their proposal?
55%.
55%. So in terms of power,
Yes.
they are arguing that their controlled duplication and more complex directory can
Yes.
give you higher energy performance
Yes.
with a little bit of better performance compared to no duplication.
Yes.
Okay, so maybe, in my opinion, if I choose the simplest one, I should choose no duplication at all with sharing. Okay?
Yes.
That gives a good performance with relatively not bad energy performance. But if they tune a little bit,
Yes.
that kind of tuning, they can improve a little bit. Do you have your own idea for this idea? Can you come up with better idea? You are 99, right? I remember your midterm exam, right? So, can you come up with better idea?
Actually, I haven't think about.
You haven't thought about that?
Yes.
Maybe you need to think about
Yes.
because, right, so implementation takes a while, but actually their idea is not bad, frankly, okay? Because you need to distinguish private and shared, because they are sharing, there's quite an amount of overhead. And how you can share, they propose one solution, right?
They. How can share?
Right, for the sharing, they actually control this duplication.
Yes.
Right? So they sometimes allow restrict sharing,
Yes.
and they can give you better energy performance in addition to a little bit of higher performance. The performance which they did not convince us because it's only 3%,
Yes.
right? But there can be other issues. As I said, private and shared section, you can change this depending on the application. Whenever you run the application, you can change the private section and shared section because it depends on the application. The performance will be quite different. Okay, you can make it more flexible.
Yes.
Okay, and each cache item can be also transit from shared state to private state, and then you can make it flexible. And node duplication sometimes is quite simple, right?
Yes.
So you can combine or you can think about another idea, right? So because you are following my class, quite well. You're from computer electrical engineering.
Yes.
So think about, and if you propose a good idea, I will give you bonus points. And maybe you can work on this idea also. I'm just suggesting. Okay, so you don't have to be responsible or obliged to do this. You just give me your idea whether you have thought about this issue or not. Okay, what others?
Backside presentation.
Okay, so let's go to the next slide.
Also suggested some modified version of controlled replication because they show less energy consumption and 7% performance degradation. Tag directory buffer uses small full associative buffer to hold clean lines. It handles read requests for clean lines. Using tag directory buffer, controlled replication design can be looked like as shared design model.
So they suggest this new structure called tag directory buffer.
Yes.
Okay, so using the buffer they can improve a little bit.
Yes.
Okay, skip. Sharing migration seems like what I have mentioned. Is that right or different? No? Copying with shared line to the home relation type.
When cache to cache transfer by using directory, directory have to check where the cache line is in.
Which is?
Yes. So by sharing migration, directory can find directly because it's home tiles directory find in home tiles line. So it can reduce pending state.
Okay, so there is usually home directory because directory information should be somewhere, right?
Yes.
And then sometimes shared line can move to the home directory
Yes.
so that you can accelerate a little bit.
Yes.
That's what they are suggesting.
Last one is modifying coherence protocol and directory hardware to allow parallel read.
Okay, skip.
Yes.
So how much they can improve by those optimization? 1%?
Actually, tag directory buffer has two variations, which is tag directory buffer all and tag directory buffer. It is separated by line which is in tag directory buffer has.
So overall, how much do they improve? Approximately 1%, 2% or what?
Compared to shared version, 3%, but compared with controlled replication, 10%
Okay,
performance.
so overall for compared to normal or new duplication, the performance was only 3% additional gain.
Yes.
So how much do you think they can gain from this optimization in addition to 3%?
Excuse.
Okay, so in the previous picture you gave me two pictures. One is performance, one is energy, the other is energy. For performance,
Yes.
the only additional gain is only 3% compared to.
That 3% means this bar with tag directory buffer.
Okay, so all combined. Okay, with this scheme already.
Yes.
Okay, skip. Okay, skip. Okay, thank you. Okay, let's have a 10-minute break since we don't have much.